Hey, welcome back everyone. So I believe I owe you guys an apology. I haven't released a video in a while, and I'm sure you're eagerly awaiting for part 2 of the infinite square well problem. But yeah, a lot of my focus has been, consolidated in this mentorship program I've been working on, and I've sort of been investing a lot of that time working on that, as well as learning some new things, stuff that has sort of caused me to really sit down and just delve into some stuff that I haven't been able to sort of use for the part 2 video, because I maybe bit off a little more than I can chew. I'm trying to incorporate some new filming techniques, and that has proven a bit of a challenge. So I realized I needed some prerequisites before I could fully invest in the new kind of filming that I was seeking to do. But with that in mind, I figured I may as well show you guys a little bit of what I'm working on in my mentorship program. And lately we've been doing a lot of numerical calculations, and that is what I'm going to be showing you today. And this method is known as Euler's method, and it is a technique for solving differential equations that is effectively an approximation. And because that's what engineers and physicists do, mind you. So with that in mind, as you can see on the board, I have a differential equation and an initial value condition. So we're going to be solving this, finding the exact solution, as well as approximating it with Euler's method, so we can compare the two to see how close they are, given the step size and the approximation that we're working with. So first, I'm just going to sort of briefly go through the algorithm for what Euler's method is, and then we'll solve this for the exact solution. So Euler's method is effectively this. You have your y value at some nth interval is equal to the preceding y value, n minus 1, plus some step size we'll denote as h, and then some function where the arguments are also taken a step back. So in our case, we're working with t and y, so we're going to have t n minus 1, and then y of n minus 1. And that's basically it. We just kind of feed itself into this problem. It's sort of like exploiting the initial value condition. So you do have to start out with one general assumption. And this is the assumption that we're going to be making. So basically, we're going to have our y for our initial condition, y equals 1. And then for t, since t is our argument there, is going to be equal to 0. And then our step size, we'll just start out with the 0.1 for our step size. So 0.1. Now, I believe it would be helpful if we came out with some intervals at, like see how far we want to take this. So for t, we'll just move up in steps of 0.1, okay? So we'll go from t, start at 0, then 0.1, and 0.2. And that can really just go on as long as you want. I'm not going to do a bunch of intervals because I'm going to be showing you how to do it on the computer afterwards. So I'm just going to show you a few so you can get the basic idea. So for our first interval, for y1, well, that is going to be equal to n minus 1. So we take that a step back, and we're going back to our initial point, and we have 1. Okay? And then we add that to our step size, which is 0.1. And then we multiply that by our function. So our function, right here, I'm just going to rearrange it. Our function is going to sort of move all of this over, and we'll be solving for our differential part there. So we'll have our function equal to, so t and y is going to be equal to t times e to the 2 times t plus 2t. Okay, so that's our function that we're going to be using, and we're going to be plugging that in here. So first, we are taking our step size back. T is starting at 0, so this first part is going to just disappear, and then we're going to have 2 times our yn minus 1, which is just 1. Okay, so then we just sort of multiply this out and add it up, and this comes out to about 1.2. Okay, so we'll take it one step further just so you can get a feel for the behavior and the workflow of this, basically. So 1.2, we're going to feed that back in to our next y interval. So now we have y of 2, and then take that to our previous step, which is going to be 1.2 plus 0.1. And now, since we're moving up a step of 0.1, that is going to now give us something to work with. So for t, it's going to be 0.1, and that's going to be multiplied by 2 times 0.1, and then plus 2 times 1.2. Okay? Now, we go through that and solve it. It's going to come out to about, let me check here. It's going to come out to, that is going to be 1.45. Okay? So 1.45, roughly speaking. So you can kind of see how this will go. If we go up to another step to y3, y sub 3, then 1.45 will be substituted back in there, as well as this y part here. 0.1 will move up to 0.2, and so on and so forth. So now we can see how that works. This is going to be the algorithm we're going to be constructing for the computer to solve for us, because this is just screaming computation. This is what computers love to do. So let's first, now that we kind of got a feel for the sort of algorithm and how Euler's method works, let's just solve this analytically and get an actual solution that we can compare it to. And that's how we can sort of verify how effective Euler's method really is and determine whether we need to adjust our step size at all. Okay? So, move this out of the way here. So, let's first, to solve this with some of our analytical techniques, we need to find our integrating factor. So our integrating factor is going to be this right here. So our integrating factor is going to be equal to e raised to the integral. So minus, we'll just put the minus on the outside. We've got to make sure that's there. 2 dt. All right. So easy integral. That's just going to be e raised to the minus 2t. Okay. So now that we have our integrating factor, we can start constructing our general solution here. So we'll have y in terms of t is equal to, so we're going to have this sort of the inverse of this quantity on the outside of our integral. So we're going to have e to the 2t, and then we'll take another integral, and we'll be grabbing this component along with this. This is what we're going to be integrating over. So we're going to have e to the minus 2t multiplied by t times e to the 2t dt. Alright, so now what we can do is pretty simply just cancel these out. Those are just going to, cancel out to 1. And this now will give us e to the 2t, where we have some integral of t dt. And that is going to be equal to e to the 2t. And we'll now have 1/2 t squared after taking the antiderivative there. And that is going to be added to some constant. Okay? Some constant of integration. Now, we want to solve for our constant of integration. Fortunately, we have our initial value condition. So let's sort of plug that in. So Since y is now going to be equal to 1, t will be 0. So 1 is equal to, this will cancel, this portion will cancel out. And e to the 2t multiplied by 0 is just 1, so c is equal to 1. Easy peasy. So our exact solution now, so y of t is going to be equal to 1/2 t squared e to the 2t plus e raised to the 2t, and that will be our exact solution. Great. So I'm going to bring this on over to the computer, and we'll see how well Euler's method stands when we have our exact solution, and see just how accurate it really is.
Alright, so here we are on Jupyter Notebook, and also you might be noticing I'm wearing a headset. That is because the microphone on my camera isn't working so well, so I hope this isn't too much of a nuisance. But so first here, as always in any sort of initial point when you start coding, you want to import the necessary libraries. So import numpy as np, and then import matplotlib.pyplot as plt. And we're importing the matplot library because we're going to be plotting, just to get a more visual understanding how well Euler's method works. So first we want to define our functions for our initial function, before its exact solution, and then we want to define a function for the exact solution as well. And so the first function, so we'll call it dy dt, and that is going to have arguments t and y, and this is just going to return, what was it again, 2y, so 2 times y plus t times e, or np dot exp, p raised to the 2 times t. Alright, so I think that's the correct equation. Yes, okay, cool, just to make sure. Now we want to define our exact solution, so we'll define that as exact, where we have just t now. That's the only variable in our solution, so return that as, so it's 1/2, that's going to be multiplied by np.exp to the 2 times t, and that is going to be plus, and then we gotta forget that t squared plus np.exp 2 times t. Alright, so that should be our solution. Yeah, that looks good. Cool. Alright, so now we have our functions, we can start writing the bread and butter of our code here. So first we're just going to define our function as Euler, and we're just going to have some function that we're going to be inputting, because that's going to be the only positional argument that we need, because we're going to have the user prompt and indicate, we're going to have the user prompted and then indicate whether they want a different step size or not, so we have that kind of freedom. So first let's define our step size. So we'll call that h equals, so because our step sizes are going to be in terms of floating points, so I'm going to have float, and then input are there, so that's going to be select a step size. Alright, and close that off. So then we're going to have an array of t values, and this can be changed to whatever, but we're going to go from 0 to 0.6, and we can obviously increase that to see how well Euler's method behaves further down the step, further down the array. So np.arrange will have from 0 to 0.6 in steps of h. Okay. Now, what we want to do is initialize a list of, or array rather, of just y values that we're going to be iterating through. So we'll have our y values equal to, we'll just do np.zeros, and for the length of this array, we'll just make it in terms of the length of our t. Alright, so we're not hard coding anything. So there's that. So now what we need to do is ask the user, prompt the user to provide an initial condition. So y0, we'll call it, is equal to int input, and then we'll have enter an initial condition. Oh, spelling today. Alright, so enter an initial condition and close this off. Great. So there's that. No issues there. No errors. So, and then we have to ensure that this value is our first element in our array of zeros. So for y0 is equal to y0. So that will ensure that our first condition is at the forefront of our array there. So now we can actually write out our for loop, okay? And it's just a simple little for loop. So we'll do for, we'll just do for I O in range of 1 to the length of t. So that's just going to span from 1 all the way through just however many elements are in the t array. And that is so we can, for each step, perform the calculation that we need for that. So that will allow us to sort of cycle through each element in the array of the y array, and then sort of feed itself into that, so we can actually calculate our approximation. So for that, we're going to have to initialize an index for y of I0 equal to, so then we want our y index I0 minus 1, okay, just like Euler's method, the equation, plus our function that we're going to be feeding into it, dy dt, but in this case we have to sort of use that same argument, so we'll have f of t, so t is going to follow that same behavior, same pattern, so I minus 1, and then our y variable, as before, I naught minus 1, and close that off, and then we have to multiply by our step size. Okay, so let's just enter this to make sure there's no errors. No errors, that's good. Cool. So now, what we would like to do is, at this point, we can calculate our calculate what the solution should be, or at least a rough approximation of it. But what I want to do is to create a plot that sort of shows all of the values and references them with the exact solution. So we'll pull up a plot, so plt.plot. So we are going to be going from t all the way, so t is going to be our x-axis, or our t-axis, along the horizontal, and then what we want is our y values. Okay, So our y values will have that there, and then let's first just enter this and return y, so we can actually get a little bit of an idea of what's sort of going on here. So we'll return that. So let's try it. Euler, and we will put our dy dt in there, and sorry, so select a step size 0.1 and initial condition 1. Alright, so cool. So we actually have our array that gauges, or it gives us the first three values that we calculated before on the board. So we have 1, so our initial, 1.2, then 1.45 roughly, and then it keeps going. So that's great. So this works very well. So now what I think we should do is plot the exact solution. So we'll have plt.plot again, but this time we're going to have our t values for our exact solution. So exact of t. And we can see just how close it is here. So step size 0.1, initial condition 1. Alright, so so we can see that they aren't, that close, but they give us a little bit of an idea of what's going on. So let's create a legend here. So let's make sure that this is labeled equal to the approximation. Okay, and then this label equals exact solution, and plt.legend, and then plt.show. Alright, so we can also create our x and y axis labels, which would probably be good. So plt.xlimit, or x label, we'll have that as just t. And then I'm just going to copy that, and this will be y for the y label. Actually, rather, we'll just have this y of t. Okay, cool. And we can actually put this in some fancy LaTeX sort of format. And so 0.1, initial condition 1. Alright, so we have our approximation, our graph y of t, and then our t-axis labeled here. So now at this point you might already be able to guess that we could also create a better approximation if we reduce the step size. So let's say we reduce the step size just another order of magnitude, just to see how close these end up becoming. So we will have now 0.01, and then our initial condition of 1. Oh, there we go. So now you can see just how much closer these curves are to each other. So that gives you a pretty clear indication. If you go one order of magnitude, that if you go up one more order of magnitude, I mean, it'll basically be an exact solution. And obviously you can see all of the values plotted out here, or printed out here in this array. So this gives you a pretty good idea. You can actually provide a what am I trying to say? You can provide an error approximation. So we'll have error. So error is equal to np. We'll do np.subtract. Okay, and we'll say we have our so y from let's just do five steps, and then subtract that from our exact. Let's see, we'll have our exact of t, again, 0, 5, and that should give us our rough error here. Have to do an absolute value there. So we'll start with 0.1 again. Look at that. Oh wait, we gotta return our error. So 0.1, 1, return our error. So we basically have our error. We gotta make sure we take the absolute value of that so we can get a better idea how that's looking. We'll just do this. Okay, cool. So 0.1, 1. Oh, we need that there. 0.1, 1. There we go. So now we have our error. We can see roughly how well our, how close our approximations. As we get higher and higher, though, you can start to see that our error gets worse and worse. So, like, you go up to 0.02. So, like I said, like before, this was pretty close, for its initial condition, or at least the first few elements. But as you move up higher and higher steps, it starts to diverge a bit in terms of its accuracy. So that is Euler's method. I hope you enjoyed this, and again, I'm sorry it's been a while since I've released a video, but I will be sure to do more videos like this in the future, and I assure you the infinite square well problem part 2 is coming soon. Thank you.